Right. Good afternoon, everyone. Welcome and thanks for attending today's presentation. My name's Dan Whitley. I work for Briggs & Forrester. I also sit on the CIBSE Merseyside and North Wales Region Committee, who've pulled together the Masterclass presentations this week. So today we have Laura Bishop from Infinitas, who's done a talk through us on heat pumps technologies. So without further ado, I will pass over to Laura and she will take you through it. If I can ask if everyone can keep the microphones muted, cameras turned off, and any questions, if you put them through the chat function, and I will liaise with Laura through the course of the presentation. Thank you very much. Cheers.
Thanks, Dan. Yeah, thanks for the opportunity to speak at these masterclasses this week. As Dan said, I'm going to be talking about heat pump technologies today. There's a lot that I could talk about actually, so I'm going to compress into about 45 minutes or so, sort of the technology information and some stuff about the political environment as well, costs and challenges and opportunities and things like that. So just go to my first slide. So yeah, as Dan says, about 15 minutes or so, I think, at the end for questions. So please do send through any questions, and if there are any outstanding at the end of the presentation that we've not got to, then I'm really happy to answer those afterwards as well. So just a bit of background about myself. So I'm a chartered mechanical engineer with the MIMechE. And about 8 years ago, I left E.ON to set up my own consultancy, which specialises in renewable heat systems. We've done a lot of biomass over the years, but now we are doing much more heat pump work. We try and put ground source in as much as we can, or design ground source systems, but we also do air source systems, and they tend to be on the more commercial industrial side. And we also heating cooling network consultants as well. I'm currently chair of the Ground Source Heat Pump Association, which represents the ground source industry in the UK. We have members from installers, consultants, designers, drillers, suppliers, all sorts of different people. We're getting a lot of interest as well in members from councils and government as well, because of the interest in ground source systems. And I am a complete heat pump advocate. As I say, I am an engineer, so I do come from a sort of approach things from a technical, common sense point of view, and having worked on lots and lots of different systems over the years, heat pumps is what I've plugged for, and I do believe that they are the way forward for electrification of heat. So all the things I'm going to talk about now come from that knowledge that I've gathered over the years. So hopefully today will be of use to you from sort of what I've learned and what I understand the current environment for heat pumps. So on the agenda, as I say, there is a lot I could have talked about. If anybody was on the I did a presentation for CIBSE back in December. So sort of the agenda is pretty similar, but updated for where we are in March. So we're going to cover very basic heat pump information. We're going to look at some heat pump applications and a couple of case studies. We're also going to look at the political landscape, heat pump policy, and where we are with that, incentives, grants and things. Finally, we're going to look at the challenges and opportunities that we are faced with in the heat pump industry. So the first point on the agenda is heat pump basics, what and why. So what is a heat pump? So the heat pumps we're going to talk about today are vapor compression cycle heat pumps, and because this is a technical seminar, I'll go into a bit of detail, but I'm sure some of you on here will already be aware of this. So a heat pump is essentially a refrigeration cycle machine. That little picture you can see in front of you basically shows the four elements of a heat pump. We have the evaporator and condenser, which are two heat exchangers, the cold side on the evaporator and the hot side on the condenser, and then the other two components are the compressor and the expansion valve. The compressor is the item that uses electricity. So a heat pump is an electrical heating and cooling machine. So what we've got going on here is in the blue and red lines, that's refrigerant, and that is either a gas or a liquid, depending on where we are in the cycle. So if we start on the left-hand side, I am trying to get this animated at the moment just to help understanding a bit, but I'm sure most people watching will know what I'm talking about. So we have the evaporator, which takes in the energy that's free and available, whether that's air, ground, like brine coming out of the ground, or water coming out of the ground, or the river, or mine water, or wastewater. That's what the evaporator is doing. It's absorbing energy from outside. That's then the refrigerant is then passing into the compressor, where it is compressed to high pressure, and it's be high pressure hot gas at this point. That then goes into the condenser, where it gives up its energy to the heating system. If it's working in reverse, that's where it gives up its cold to the cooling system. So that's going into your hot water cylinder, or it's going into your underfloor heating or your radiators. That's then still gas, but low pressure, low temperature, and then it goes through the expansion valve back around into the evaporator, where it starts to pick up the heat again. So it's continually circulating. It's a closed loop system, and it is at different points that it'll either be a hot gas, a cold gas, a hot liquid, or a cold liquid, depending on where it is. But that's the system that goes around and around constantly. Fridge freezers work on exactly the same principle. So a fridge freezer is a heat pump, essentially. Technology has been around for a very long time. The vapor compression heat pumps were actually, I believe, invented in 1946, but the principles of this system date back to the late 1800s. So when people talk about heat pumps as being a new technology, that's not the case. They might be new to a lot of people now because they're in the media quite a lot, but they're certainly not new. And anybody that's been working in the heat pump industry, we've been putting them into the UK since probably the 70s, definitely into the 80s and 90s. We've got thousands of heat pumps in operation around the UK of all different types, air source, ground source, water source. But because they've only recently come into the mass media, that's why some people are saying, well, this is new technology. How does it work? Is it going to work? If you look at Scandinavia and Europe, they have been using heat pumps for a very long time. And they're a very different political landscape over there and economic landscape, so that's why heat pumps has worked for them over there. We are on the back foot a bit in the UK, running to catch up, but certainly not new technology. And the heat pump itself is actually a very simple system when it boils down to what you're looking at here. So a heat pump, it converts low grade free energy, and that's the important bit, into high grade useful heat, hot water and cooling for whatever application you've got. The trick is to minimize the electricity going into your compressor, because that's what you're paying for, and to maximize what's coming into your evaporator, whether that's from the air or the ground. And that's going to be constantly changing, but that comes down to your design. And it would be good actually if we could have, if we had a bit more time, I would go into that in a lot more detail, because it's important to understand about how you can maximize your efficiency or your coefficient of performance, COP. So why heat pumps? Why now? Because of net zero. That's essentially what this is all about. But I think recent events over in Ukraine and Russia have also focused our attentions on energy security. So the Committee on Climate Change, the CCC, state that around 31% of UK emissions come from heating our buildings in the UK. Some of the people say it's 23%. It's around a quarter to 30% of all emissions. So it's the biggest emitter by sector, heating UK buildings, not just houses, but all kinds of buildings, commercial buildings, industrial buildings. So it's a big area to tackle if we're going to get to net zero. So this is all about decarbonising the heat that we generate. 85% of homes in the UK or in England are on the gas network. So it's a huge undertaking to take them away from a gas system onto a heat pump system. But this is the path that we are now on with the government, because we have these legally binding 2050 net zero targets. We can't escape from them, even though sometimes we don't hit our carbon budgets. In fact, I think the last one or even two we didn't hit, but the target of net zero by 2050 is there, and it is legally binding. The government have announced and been very clear that they see the route for decarbonising heat to be electrification. So this is the main route to decarbonisation. It's not the only route, and most people on the call will know about hydrogen, energy from waste, biogas. There's lots of different ways of doing this, but the government have been very clear that electrification of heat is the key route forward for the UK, or certainly in England, and I think Scotland and Wales have got very similar targets as well. Heat pumps as well, another side benefit is that you have clean air because you're not combusting oil or gas where the building is. So you benefit from clean air. Of course, if you're still using gas or coal to generate electricity, there will be problems with lack of clean air at those power stations. But as we've seen the grid decarbonise over time, clean air will become more prevalent. But as soon as you take a gas boiler out, put an air source or ground source heat pump in, you are immediately improving air quality around that building. And the reason that we believe heat pumps is the way forward is because they are so flexible. There is a perception, I was at the Low Carbon Agricultural Show yesterday presenting on how heat pumps can be used in agriculture. That's in so many different ways, but there's still, I think, a perception that heat pumps are for houses, and I think that's partly to do with the media. So when people talk about heat pumps right now, they actually mean air source heat pumps, and people think air source heat pumps for houses, and actually heat pumps can be used in, as I say, many different applications. So let's have a quick look at, oh sorry, no, I do have another slide on why heat pumps for net zero, just to demonstrate what was on the previous slide. So this is looking at carbon reduction. Just click forward. This slide here is a representation of a house, a nominal house with 5,000 kilowatt hours per year heat demand. And there's a few different options there along the top that you can see how using different types of heat generation systems can save or increase carbon emissions. So on the first column there, we've got a gas boiler, nominal seasonal efficiency about 93%. The carbon emissions using 2021 government carbon figures is just under a tonne, or 983 kilograms per year for that gas boiler, delivering 5,000 kilowatt hours per year to that house. So obviously there's no saving on that, that's our baseline. If you were to put in an air source heat pump, I've used a very conservative efficiency or coefficient of performance there of 2.9, but we do have to be aware that with air source, when you need the most heat is when they are at their least efficient, because the outside air temperature is low, and you've also got to take into account defrost cycles. So your overall efficiency in the year is not going to be as high as it would be with a ground source. But we do know that the majority of heat pumps going to go into housing over the next few years will be air source. So efficiency of 2.9, carbon emissions using, again, 2021 government figures for electricity, 362 kilograms per year, and a saving of on gas of 63%. So even if everybody put air source heat pumps in, ignoring the impact on the national grid, you'd straight away get a saving of 63% on baseline. Moving across to the right, you've got then two different types of ground source. You've got one operating at an efficiency of 3.5, one operating at 4.5, and you can see the impact on the gas baseline, 69% and 76% saving on carbon emissions. And that's just demonstrated in the table at the bottom there. I've put in the top line there, GSHP, so that's ground source heat pump at 2030. And the reason I've used that is because the future scenarios for National Grid show how they think the grid will decarbonise over time. So by the time it gets to 2030, the grid carbon intensity should be probably just below 100 grams of CO2 per kilowatt hour. So they are anticipating the grid continuing to decarbonise as we get more wind, more solar, more battery storage, so that we can use less gas and certainly hopefully get less coal. So let's have a look at some applications. This is just a sample of photographs for different kinds of heat pumps. The top left there, we have got two NEBE F1345 ground source heat pumps, 240 kilowatt units in parallel there, doing 80 kilowatts for and this one it was 2 domestic houses. Top right there, other end of the scale, although not as big as they can go, we've got 800 kilowatts of heat pump for heating and hot water. This is for a college in Scotland with a heat main attached, doing 5 plant rooms. So you can see it's very industrial compared to the more domestic ground source heat pumps top left. And then at the bottom, most people are familiar now with the domestic air source. This is a Valent propane heat pump. We're having one installed next month. And those, so you can see the variety of different kinds of heat pumps that you can buy. As I say, most people most familiar with the domestic air source units there, and you will start to see them popping up more and more on people's houses. But as I mentioned towards the start, heat pumps are really flexible. So you can have the size of a heat pump, anything from a 3 kilowatt unit, a little tiny shoebox unit that might go into a small flat, all the way up to 8, 9, 10 megawatts plus, especially when you are cascading heat pumps together in both air source and ground source. Although when you start to get to the much bigger commercial systems, ground source starts to make a lot more sense. The resource you can use is really flexible too. You've got the choice of air, which is obviously everywhere. You've got water. So if you have, we're working in a factory at the moment, which is next to a river. So we're doing some open loop water source with them on the river. You've got ground, which could be vertical boreholes. It could be a horizontal collector, cheaper, but need a lot more land. Vertical boreholes, more expensive, but much smaller land area required. You can have open loop ground source, which is where you drill into an aquifer and you take water directly out of the ground. You can use waste heat, you can use mine water. There's the CEng Garden Village project up in the northeast, which is the first one to be using mine water on a large district heat network. Wastewater, so extracting heat from sewage. There's so many different types of resource that you can use, and you can also hybridize them together. So there's a job going on in Cambridge at the moment, Swaffham Prior. That's a 330 house village going off oil and onto a mixture of ground source and air source with some electric backup boilers. So they're really, really flexible in terms of the resources you can use. And in terms of temperatures, most people I think would say, oh, the heat pump can only do 40 degrees C. Actually, depending on the refrigerant and the type of heat pump you're using, you could have anything from 30 degrees C up to 90, 95 degrees C if you're using something like ammonia. So it's about having the right heat pump for the right application. Of course, heat pumps can do heating and cooling. So if you're traditionally having a gas boiler to do your heating and a chiller to do your cooling, the same machine, you can have a heat pump that will do both, and you can either have it doing heating or cooling, or you can have it doing simultaneous. So it can be a saving on plant, because you can have one machine instead of having 2 separate machines. I was talking to somebody yesterday who actually replaced a air to water chiller, replaced it with a water chiller to do, I think it was like a cooling plant, a food storage plant. So they're still doing the same amount of cooling as they were doing before, but instead of chucking all the heat out to air, they're now extracting that heat from the reject heat and putting that into the heating of the building. They no longer need to have, it was actually LPG boilers, so they've got rid of the LPG boilers, and the water source cooling system is now doing all of the heating and most of the cooling in the factory. They're great for new build and retrofit. Lots of talk in the media about putting heat pumps into older buildings. One of my specialities is putting heat pumps into older buildings. So certainly suitable for both new build and retrofit. Easier in new build, of course, because you design your building for low flow temperatures, but it's more of an engineering challenge for retrofit, which is why it's more interesting. So any engineers on here, if you come across retrofit projects, they are great because they're so interesting, and heat pumps work brilliantly in there if you do it right. They are suitable for houses, offices, leisure centres, mixed-use developments, housing estates. Yeah, I've talked about leisure centres, schools. There's lots of schools going on at the moment that are going off gas or off oil onto air source heat pumps. So they are flexible to be used all over the place. Yesterday we were talking about grain drying, potato drying, dairies, so they can be used in industrial applications as well. And of course, they're great for use in both 4th and 5th generation heat networks. So 4th generation is lower temperature heat, sort of maybe 55, 60 degrees C in a network, and 5th generation ambient loops. And we'll talk about that a little bit in a second. So a couple of case studies here. This is a job that went in a couple of years ago. It's a rural village in Oxfordshire, 26 houses owned by the landowner. The houses were very poor in terms of energy performance certificate, the EPC, and once the tenants had moved out, they would not have been able to re-let the properties. So some of the houses were on oil, some were on LPG, some were not heated at all, some were still using coal fires. So what they decided to do, the landowners, they decided to go down the ground source heat pump route. They would get renewable heat incentive, which they'll get for 20 years. This is a energy centre, which you can just see at the bottom right there. And then the energy centre has got 6 60 kilowatt NEBI heat pumps in there, so 360 kilowatts of capacity, coupled to a horizontal closed loop ground collector. That's in the field at the bottom there. That's all you can see after the field has regrown. So you don't actually get anything left over apart from the black caps you can see there, which is the manifold covers. That is then delivering heating at 55 degrees C into a heat network. You can see that in the red lines on the picture on the left-hand side. So brand new preinsulated pipe, taking 3 legs, taking to different parts of the village. And really interestingly, we were on site with them 2 weeks ago. So 55 degrees C, not many radiator upgrades. Of course, if they didn't have a heating system, that had to be put in new. But many of the houses that already were using oil, they didn't have the radiator swapped out because the landowner just said, well, let's see how it goes. He's obviously not living in the houses, but when I walked in, this is 2 weeks ago, so it was still February at the time, nice warm house, warm radiators. So the myth that we perpetually come across, which is that you've got to rip all your radiators out and rip all your pipework out, is not true, as proven by this. Sometimes you do need to do it, but it's not a given, it's not a prerequisite for a heat pump. So these houses here, 26 houses, they date back to 1800s, you know, not great fabric, but they have put in some double glazing where there was none. So anyway, the tenants are now benefiting from clean heat. There's HIUs gone into each of the houses with heat meters on, and they're paying a fair price, like a fixed price basically, to the landowner for the heating and hot water. We're now looking at extending the network. There are private homeowners in the village that are looking to come onto the network and decarbonise because they're all on oil. This is an off-gas village. So that's an example of where ground source can be used in a rural setting. This is the other end of the scale. This is an EBTEC Energy Systems project, one of the GSHPA's members, soft fruit grower Hall Hunter partnership. This is an 8.8 megawatt heat pump system, and it's a water source heat pump system. So they're taking water out of the River Loddon, about 640 litres per second on average, and they are distributing heat around to several glass houses, 110,000 square metres actually, and they're growing strawberries for Marks and Spencer's. In the first 6 weeks of operation, they delivered 5,000 megawatt hours, 5 gigawatt hours of heat from the heat pumps. I haven't got any figures actually on the efficiency, but because it will be a low temperature system and they're taking water out of the river, which is a slightly, well, it'll be higher than air source certainly. What we do know is that they will save 44,000 tonnes of carbon over 20 years. And the guys who own it, Hall Hunter, are so pleased that they were looking to install a further 8 megawatts. Again, they're claiming the renewable heat incentive, so that's helped the project finances. But this is just an example of 2 different types of system, 360 kilowatt ground source up to 8 megawatts plus. And then of course you've got the very small sort of domestic level heat pump systems as well. I think I'm going to have to get a move on. So 5th generation, we've talked about ambient loops. So this is where you have a cold heat network, 5 to 20 degrees C. You can have heat coming in from different sources. It could be a borehole system, it could be a river, it could be mine water, it could be some waste heat from data centres. And then the buildings are extracting that heat and using that, also not that heat, that energy, using it within each of the buildings for whatever that particular building needs. So one building might need cooling and reject heat back into the network. Another building might need heat at low temperatures, in which case you have a low temperature standard heat pump. Other buildings might need high temperature heat pumps, but they could all use the same energy. You've got to balance the network, but heat pumps are absolutely great for this kind of system. So what about hard to heat buildings? people always quote, you know, we need to put cavity wall insulation in, we've got no loft insulation, we've got no double glazing, but there's stacks of examples of where heat pumps are being used successfully in those kind of difficult buildings. Of course, fabric first is recommended because you reduce your peak and annual demand, so you can have a smaller heat pump. But if you can't do that, it's not a showstopper, and I always refer back to people like the National Trust who've got heat pumps installed in their stately homes. They are completely grade 1 listed, can't do any fabric improvements, but they have heat pumps working very efficiently and very effectively. But you do have to design it correctly. You have to take in the building as a whole. So taking a holistic approach to a building, understanding the way it's using heat, the way it needs to use heat, and then picking the appropriate heat pump for that. You can also change the operating conditions, so operating low and slow. So have the heat pump on all the time, background heat. Low temperature, I'm talking maybe, I don't know, 50, 55 degrees, or maybe even lower. And sometimes you need to keep an eye on how the system is operating. You can reduce your temperature lower, as long as you don't have those spikes of heat in the morning and evening, as we do sometimes with gas boiler operation. You do have the options of high temperature heat pumps. We talked about those earlier, ammonia, CO2 heat pumps, going up to 75, 80, 85, 90 degrees. But of course, your COP, your efficiency will be hit. So if it's a very difficult building, you can still decarbonise, but you have to be aware of the impact on running cost. You can also look at hybrid and biovalent systems, and I can go into that in more detail another time, which is sort of coupling up things like ground source and air source, working out when it's more efficient to run one or the other, or even to still have gas boilers on as backup or peaking load. So a quick look at whiz through where we are with policy. So back in November 2020, Boris announced his Green Industrial Revolution 10-point plan. Straight away that happened, that was just after I took over as chair of the Ground Source Heat Pump Association, and all of a sudden the conversation around heat pumps completely changed. You've got people now not asking what is a heat pump, but they're asking how can I have a heat pump? How does a heat pump work for me? Certainly there's been loads of stuff in the media, and I'll talk about that a bit more at the end. We have had for the last 10 years, actually 11 years now, we've had the domestic and non-domestic renewable heat incentive. The domestic one ends this month, March 22, and the non-domestic right try actually finished last year, although there are still extensions and tariff guarantees running out until March 23. The domestic right try scheme has sort of been replaced by the boiler upgrade scheme, which launches next month. That is an upfront pot of money to be given to anybody who wants an air source or ground source heat pump. £5,000 for air source, £6,000 for ground source, drop in the ocean for ground source. But we do know that obviously the main bulk of domestic heat pumps will be air source. There's also the public sector decarbonisation scheme running out at the moment. The next scheme, PSDS 4, I think the application's going in April. I have lost track a bit of those, but that's funding public sector buildings to decarbonise. We had the heat and building strategy released in November last year, finally, and that talks a lot about heat pumps. However, we're still waiting for the actual roadmap and policies to make what's promised in the strategy actually become a reality. But on the back of those, there were some consultations. Key ones to be aware of are these two here. The consultations were about phasing out the use of non-gas boilers, so oil and LPG specifically. So we're waiting for the results of the consultation to be announced by government, but their plan was that from 2024, all large buildings greater than 1,000 square metres, this is commercial buildings, will not be able to buy or reinstall LPG or oil builders from boilers from 2024. And from 2026, everything else, so houses, commercial buildings, industrial buildings, from 2026, you will not be able to buy an LPG or oil boiler. It will have to be a heat pump first approach or a good reason not to do a heat pump. So we have the carrot with the RHI, this is the stick. So hopefully what we won't see is in 2025, everyone going out and buying oil and LPG boilers to last them for the next 10 years. But we do need to make people aware that this is coming, because 2024 is only 2 years away, so quite quick. Innovation, in terms of what's happening in innovation in heat pumps, one of the big things people are working on, we're working on, is the reduction of capital costs, because it is expensive to have a heat pump. Shed ground loops, that's with ground source in particular, shared ground loops is going to be the way that we are going to see mass rollout of ground source heat pumps. Individual ground source heat pumps on individual houses is really expensive. Some people are still doing it, you know, particularly more well-off people. But if you're looking at shared ground loops or central ground source heat pump systems on a heat network, that's where we can start to see real efficiency gains, and that's where they work extremely well. Flexible heat tariffs, that's a bit of a strange one right now because of where we are with electricity and gas prices shooting up. This is a very unusual situation, but Octopus and people like that were offering flexible heat tariffs specifically for heat pumps and also for electric vehicles. The use of thermal and battery storage, I could do a whole session on this. So other than to say storage is going to be extremely important, especially if you're going to start looking at demand side response for heat pumps, that's switching them off at times of grid stress and switching them on when there's too much power on the grid. If you've got good, well-designed thermal battery storage, you can actually really make some inroads into your running costs on heat pumps and also revenue from demand side response. And the use of low global warming potential refrigerants. We're still seeing most heat pumps probably still on R407C 134A. We are seeing though now a lot more heat pump manufacturers going over to the more natural refrigerants, low GWP, so propane, CO2, isobutane, and we've got this one, the HFO R1234ZE. So if you're specing heat pumps now, you should really be looking at these kind of heat pumps and not the traditional HFC heat pumps, because they are going to be phased out over the coming years. And still a lot of innovation going on with high temperatures and higher COPs, staged heat pumps. So, you know, ammonia heat pumps have been around for a very long time, 90 degrees, 95 degrees C, but the COP does suffer. But we are starting to see, with the use of new refrigerants, higher temperatures being possible with higher COPs. Okay, so challenges and opportunities. I thought I'd start with the challenges because that's the bad news, and then go into the good news, which is the opportunities. So I think the four main challenges that we have in the heat pump industry are these four, and these are the ones that we talk about most. So we have the running cost of heat pumps, which is the gas and electric price. So up until recently, this used to be a conversation about how cheap gas was and how expensive electricity was. Now we're talking about how expensive gas is and how expensive electricity is. So it's quite a different conversation, but it still doesn't help the operation of heat pumps, the running costs. Capital cost, as I say, much more expensive to put a heat pump in than it is to say just put a replacement gas or oil boiler in. We have challenges around skills and training, and we also have challenges around the myths, and I put the myths in capital letters because it is a thing and it's something that we battle against all the time, almost on a daily basis. The same myths, the same misunderstandings come out about heat pumps, and we just have to keep on giving the message across that these are myths. Of course, I don't ever paper over the cracks. There are challenges and we have to be open and frank about them, but a lot of them can be overcome with good engineering practice, good design, good installation. So first of all, running costs. Traditionally in the UK, we have had amongst the cheapest gas prices across Europe and the most expensive electricity prices across Europe. And I used to present a graph to show that. Last week when I was at Future Build, somebody came to talk to me. They were paying 9 pence per kilowatt hour for gas and 35 pence per kilowatt hour for electricity. So in the past month, we've seen obviously unprecedented times in terms of costs. The fact that gas price is increasing should help heat pumps, because when you're trying to stack up a heat pump running cost against gas, it doesn't stack up. It does not stack up. So if I just show you this graph, this chart, sorry, that harks back to the one I started with looking at carbon, we're looking at actually swapping out the gas boiler that you've got in your home for an air source heat pump using gas price. I think I used the gas price here of 5 pence a kilowatt hour and electricity price of 20 pence a kilowatt hour. You can see in that chart there that although by going to a heat pump you're decarbonising, by going to an air source you're going to be paying substantially more to run the same house on a air source heat pump, and the same for ground source and the same for ground source at a higher efficiency. So, £162 on your bill. Now, if you're paying 30 pence a kilowatt hour for electricity, that's going to look even worse. So we do have this issue right now around how we make heat pumps efficient in terms of running costs. I've now heard the first set of people that are using diesel generators to run heat pumps. I mean, that is real, that's happening. We told the government, we told BEIS about this last week, that people are actually doing that, running diesel generators. Of course, it's not something that they can react to very quickly, but it is going to have an impact on being able to run a heat pump efficiently. And this is where we need to start being clever about demand side response, thermal storage, use of on-site generation, all to reduce the electricity price, the cost, sorry. Everything is about reducing the cost of running the heat pump. If you're looking at oil, by the way, that is looking a lot better, because the cost of oil in the domestic market, if you look at this, this is a snapshot from today. Boiler juice, keep an eye every day on what the oil price is doing for the domestic market. Up until about end of February, we were looking at around the sort of 60 pence a kilo, 60 pence a litre mark for oil. In the last few days, that's now shot up, and we're up at nearly £1.50 a litre as of today. So oil is absolutely off the chart with pricing. We don't know where that's going to go. We don't know how that's going to be impacted. But if you are on oil, going to a heat pump suddenly makes a lot of sense. So if you're on gas, you're probably going to pay more. If you go into a heat pump, if you're on oil, you're probably going to pay less. So that's actually why the government is focusing a lot on the oil and LPG buildings, as well as they're more carbon intensive. So that is a challenge. Capital cost, again on the domestic market, because it's very difficult to price commercial heat pump systems, commercial ground source heat pump systems, because they are so variable. But if you looked at like a standard, maybe 3-bedroom semi-house, if you had a new gas boiler right now, it costs you about £3,000, something like that, to have it installed. An air source, maybe 10, 11,000, ground source, individual ground source, 20 to 30,000 pounds. So again, not going to paper over that. There's no sugarcoating it. It's a lot more expensive to put an air source or ground source heat pump in. But if we are going to decarbonise, we need to do it. We do need grants and subsidies. Well, actually, do we need grants and subsidies? I'm not a fan of grants and subsidies. We have to just make this work. So switching around environmental levies from the electricity price onto gas, that's one thing the government is starting to talk about doing. And we do have the boiler upgrade scheme coming in April, which will encourage people to switch, because they are going to get some money up front to help soften the blow of putting in a much more expensive system. Social housing wise, we have the social housing decarbonisation scheme. So that's different again. That's a different pot of money that the government has put forward to decarbonise social housing. So we have got a few different pots. What I will say is there's no replacement for the non-domestic RHI. So these bigger commercial projects are either going to be PSDS projects, or they're going to have to stand on their own 2 feet financially, which is why, demand side response, thermal storage, battery storage, on-site generation is going to be super important for making those projects stack up financially. So skills and training, another problem. It's not just a problem for heat pumps. It is a general problem across engineering, construction generally. So it's the recruitment and it's the retention of good staff. All about competence and all about compliance. I heard a great talk last year from David, the CEO of CIBSE, talking about generally the skills gap, skills crisis in construction, and compliance is a big one of those, where you've written somebody's written a specification and something is not installed to that specification. And the number of times I've been to site where I've designed something and then found that somebody on site has decided, taken it into their own hands to size down a pipe. So I've spec'd 100 mil pipe and they've put in an inch pipe and wondering why things are not working. That's a problem. That is a real problem. And in general recruitment and retention of staff is a problem. I'm sure anybody listening to this will be saying, yeah, we have that problem. And unfortunately, because there's been no real strategy for renewables in the UK for a long time, until very recently, there's also been, unsurprisingly, a lack of investment in people training people up in renewables. Actually, 3 years ago, ground source heat pumps was taken out of the low carbon apprenticeship. So we've had 3 years worth of apprentices not learning about that. That's going to be amended in 2023 because ground source heat pump association has rewritten the apprenticeship to include ground source heat pumps. And there's a real lack of focus on design. So designing a heat pump system, whether it's a domestic system or a huge commercial system, needs some design input. And the number of people who will just turn up on site with no drawings or maybe literally a back of bag packet sketch and start building without a design or a drawing is unbelievable. And that's why we also have a problem in the heat pump industry. Not just the heat pump industry, actually, gas boilers as well, any kind of plant room. There has to be design up front, and there has to be thought going into how this system is going to work. How is it going to be controlled? What valves do we need? What size pipes do we need? How big do the pumps need to be? How big do the radiators need to be? So it's all that design, and it's a huge opportunity as well. Anybody looking to get trained up on the design side, we absolutely need more designers as well as good installers. And because of the things listed above, we end up with poor installations, which gives poor performance, and that gives poor public relations, which unfortunately does not help us with the myth busting. So I've just pulled out a couple of headlines here, two from the lovely Telegraph and one from Mail Online. These are very recent headlines that, you know, they're splashed across the newspaper. So people not in the know, which is most people in the UK, they're not heat pump experts, they shouldn't even be heat pump experts, but they see the headlines and think, well, 6 reasons not to buy a heat pump in 2022. Okay, we won't. Or it's expensive and wasteful to put a heat pump in. Thank you very much, Roy Faulkner, for your comment. And Roger Bisbee here in the Mail, heat pumps one of the biggest cons I have seen, and Boris's 5,000 grants to install them is doomed to fail. Okay. These people are not heat pump experts. I don't actually know where they get their information from. But unfortunately, things like this photo do happen, and not just this photo. So what you can see here in this photo is somebody who has not designed a ground collector correctly. The ground has frozen because too much heat is being sucked out of what they've got under the ground. And that's caused their patio, which was flat, to become like this. And this is exactly what happens when you don't design things correctly. And that then leads to these headlines and leads to the myths and leads to the neighbour talking to his neighbour over the fence saying, oh, we don't have a heat pump, it doesn't work, it costs me a fortune, it doesn't heat my house, it's really expensive and my patio now needs to be relayed. So this is, for me, it's actually one of the biggest problems is the myths caused by poor installs and poor understanding and awareness. Right, I've got a couple of minutes. So just to finish off on a positive note, the opportunities. Main point is the interest and the opportunity for heat pumps is not going away unless we have a change of government that decides that electrification of heat is not the way forward. We are not going to be getting away from the fact that heat pumps and electrification of heat is the main route for decarbonising in the UK. There's loads of opportunity for good design. So if you're a design engineer sitting on here and you have good general building services practice, then there's loads of opportunity to get involved here for plant room design, for ground collector design, hydraulic design, loads of opportunity there. A lot of talk as well about green finance initiatives. So how do we finance these big schemes or even small schemes, to be honest? So without subsidy, how do we finance, you know, green mortgages, amortizing the cost of a heat pump over the life of the mortgage, things like that. Loads of things going on there. Flexibility and time of use tariffs, and also the whole thing around thermal storage and demand side response. I think I probably mentioned it one time too many, but if we're going to make these systems work in terms of running costs, we need to be clever about the way that we are running our heat pumps, not just on off. There's a demand in the house, there's a demand in the building, so the heat pump runs. How about having the heat pump filling a thermal store up when there's on-site generation available, turning off, and then the thermal store then heats the building for 1 hour, 2 hours, whatever, depending on how you're sizing your thermal store, or using battery storage to run your heat pump when electricity is expensive, all different ways. It's all these thinking, and it comes back to the design and the planning and the upfront development of a project. Heating and cooling, any opportunity for heating and cooling together. I gave the example of the water source chiller at the start. Heat networks, government have got plans for 18% of heat to be delivered by a heat network by some date, I can't remember, 2025 or 2030. So yeah, heat pumps, as far as I'm concerned, any new housing development going in should be on a heat network. Low carbon heat network, we've just had the Green Heat Network Fund issues that started this month. So funding for developing green heat networks specifically around heat pumps. Loads of opportunity there. And obviously on the training side, the Ground Source Heat Pump Association, we're really lucky that on council we have people that are heavily involved in training. So rewriting the apprenticeship and working with the Institute for the IFA, the apprenticeship approval body. Ground Source Heat Pump Association has also developed and filmed 16 training modules, which we'll be releasing shortly onto a platform. That's a paid for training course, so that will be delivered online with live Q&A. If you're interested in that, please let me know, because that is coming. We've already had about 60 or 70 sign-ups for that. There is manufacturer-led training, upskilling courses that are happening, and MCS, which is the Microgeneration Certification Scheme, is leading on green skills upgrade with input from us and from the Heat Pump Association and other bodies to make sure that people are able to be upskilled from, say, gas fitters to heat pump fitters. So there's loads of opportunity there as well. It's just past 1:45. So I'm going to stop now. Time for questions. If anybody's got anything, I have not looked at the chat. So I'm hoping that Dan is going to put some questions my way.
Yeah, no problem. Well, great presentation, Laura. That was brilliant. We've had huge numbers today, to be fair. There was 198 people on earlier on. So there have been lots and lots of questions. So I need to apologise, firstly, everyone. I don't think we're going to be able to get through all of the questions today, just there's been that many of them, to be fair. So I will just go through now and just pick up on a few, and yeah, we can take it from there. If there's any questions which I don't get round to, that we don't answer and you would like an answer, then please drop Laura an email at email address there, and I'm sure she'll be happy to answer it. There was one question towards the end here then, which was quite good. I'm not sure you're going to know the answer, Laura, to be fair. What's the difference in embodied carbon between boilers, air source heat pump and ground source heat pump?
Actually, I'm really glad that somebody brought that up, because I did 2 exhibition or conferences towards the end of last year, and one actually just late last week, and that question's come up every single time, and it's come up again today. So it's obviously a hot topic. We discussed it at GSHPA Council 2 weeks ago, and nobody, as far as anybody knows, has done any work into embedded carbon of ground source. So what I can say is that on Monday, a few of us, like a little working group, has been set up to look at embedded carbon in ground source, not versus air source, because we don't want to say, oh, it's us versus them. It's not. But to give the facts on the embedded carbon within a ground source system. So that will include the ground collector, the heat pump itself, the pumps, refrigerant, thermal transfer fluid, all of that. So we are working on that, but we've only just started doing that on Monday. So that will be coming out, I don't know, maybe in the next couple of months. I hope so. Do watch this space, but it's something we're very aware of, and it's something that we are working on actively.
A question from Liz. Are heat pumps going to lead to increased fuel poverty? How will we stop this?
So yes, right now, as I say, if you're paying 30 to 35 pence a kilowatt hour and you're only paying 9 pence for gas, obviously already people are going to be in fuel poverty because the price of gas going up. We're paying at the moment about 3 pence a kilowatt hour, but I do know of people that are paying 6, 7, 8, 9 pence a kilowatt hour. So right now people are going to be in fuel poverty if they weren't already. By going to a heat pump, the slide I showed earlier in terms of cost difference, if you're going from a gas boiler to an air source heat pump or even a ground source heat pump, it will cost you more. There's no getting away from it right now because of the way that electricity and gas prices are structured, and because of the pressures on the energy system. So how are we going to alleviate that? If you're living in the social housing property, as I say, there is the grant funding, and a lot of social housing providers are upgrading houses in terms of fabric and putting in shared ground loops with small heat pumps in there. How they are running that in terms of a heat price, there should be a fair heat price. The electricity, I'm not sure how that's being paid for in the social housing context. All I can say is that we are all very aware of the fuel poverty issue, and right now it will cause more fuel poverty if we just go straight from a gas boiler or an oil boiler into a heat pump. Although, having said that, if you're an oil boiler, you will be better off with a heat pump system.
Yeah, okay, no problem.
If you want to send that to me, I've actually got a lot of contacts who are working on the fuel poverty side, so I can give more information on that.
Yeah, no problem. A question from Jan, but it's been sort of a little bit of a it's been a reoccurring question, to be fair. One of the challenges with the grid network, will this run out of capacity with the move over to?
Yes, so this is a big issue, and not just on the grid capacity, but also connections. So the cost of connection for a new heat pump can sometimes blow the project out of the water. You've got a £20,000 heat pump project and it's going to cost you £60,000 for a new electrical network connection. That's going to be very difficult. So there's a couple of things there. As an association, we meet with the Energy Networks Association on a regular basis, and we also have other people from other associations meeting so that we can talk about these kind of issues, find out what the DNOs are doing, find out what the National Grid is doing. But it's not like the National Grid are unaware that this is going to happen. They are aware. From a ground source point of view, we need to, it goes back to this thing around designing well. So thinking about how can you avoid all heat pumps in Britain coming on at the same time and spreading that. So use of thermal storage, again, the use of battery storage, the use of solar PV. That's going to be extremely important. So looking at a system point of view and making that point to any kind of consumer that's a really important thing they need to be thinking about. Demand side response, actually heat pumps can really help with the fluctuation of loads on the grid. So if there's a lot of wind penetration, heat pumps can all switch on, take that wind, basically absorb the energy off the electricity grid, and also switching off at times of high stress on the grid. So for example, World Cup match, everybody goes and puts a kettle on at half time. When they know that's going to happen, they can action maybe 5,000 heat pumps to switch off for 15 minutes, 30 minutes, 1 hour, provided they are set up to do so. That can actually help to smooth out the grid. What I will say about air source heat pumps is if everybody went over to air source heat pumps, I think the figure is we would need 4 new power stations. Don't ask me what the capacity of power stations would be, but we need 4 new power stations if everybody in England went across to an air source heat pump. So ground source, if possible, because they're more flexible and the COP is higher.
Yeah, no problem. A question from Alex. What's the thoughts on permafrost issue on horizontal loop systems on ground source heat pump and combating this? So
permafrost should not happen if you have designed your heat pump correctly. So that picture of the patio shows what can happen when you have it's basically too few pipes in the ground. So it's too short, the ground collector is too short. And this can sometimes happen when somebody's not designed it correctly, or somebody's undersized it because they're trying to get to budget, or somebody's turned up on site and put too short a pipe in the ground. So with the horizontal collectors, you should be going at least 1 metre down in the ground, preferably 1.2 metres. The length of pipe in the ground should be adequately sized for the load, and that's not just the peak load, it's the annual load. A good designer will look at that over 20 years and will not just look at it in day one, because over time you are going to deplete the heat in the ground. And you also need to make sure your spacing and lengths of pipes are correct and to the design. So if you do all those things, you should not have a permafrost issue.
Thanks. A question from Tom. How much impact do ground or water source heat pumps have on wildlife ecosystems due to the extraction of heat? Is there a method to quantify the potential impact?
Absolutely, yeah, it's a good question. So ground source shouldn't have an impact. As I say, as long as the ground collector has been designed correctly, you will not impact the heat or cool, the temperature of the ground, basically. The only time it becomes an issue is, like I say, if it's not been designed correctly and you start freezing the ground up. That's a big problem. So ground source, and of course, when you have reinstated the ground, as I showed in the photograph of North Aston, that field can then be used for grazing, it can be used for wildflower meadows, or it can be used for ploughing, all sorts of things. On the water source side, the Environment Agency are extremely tight on controlling how much water you can take out of a watercourse. So they're very, very careful on how much heat you're going to take, how you're going to impact the temperature of the river or the sea or the canal, whatever it is. So when you do a water source heat pump project, there is a lot of work you can do up front desktop, but the sooner you engage the Environment Agency, the better, because sometimes they may just say you cannot use water at this point. You cannot change anything in the river. Generally speaking, you can take something like 10% of the flow of the river with no problem, as in you still need to get the Environment Agency involved, and you cannot drop the temperature of the river by more than 3 degrees C or 3K. If you stick to those rules and talk to the Environment Agency up front, you won't affect the health or diversity of the river, but you do need that. That's why the Environment Agency are very, very tight on that.
Yeah, no problem. Thanks, Laura. Another question here: are there any rules of thumb for in the UK for heat from ground source, loop, horizontal, vertical, in watts per meter squared of pipe run, etc.? Something without the need to rely on a thermal response test.
So very early on in a project, obviously you do just want a rule of thumb. So there are, yes, if whoever's asking that question, if you email me afterwards, I can give you the resource for that. It's very different. You've got MCS lookup tables. So if you've got access to the MCS tables, you can use them. They're mainly for anything below 45 kilowatts, so smaller domestic stuff. I'm trying to think, there are a couple of resources that you can use, but what I will say is that once you get anywhere near detailed design, do not use rules of thumb. That's how things go wrong. So you absolutely need to engage somebody who knows what they're doing with ground collectors and get them involved. But yeah, absolutely take the point early on. There are a couple of resources that can point you at that will help you just with some rules of thumb for different areas of the UK in different geologies.
Yeah, thanks, Laura. A question from Mike: are there currently any air source heat pump, and I'll add in ground source heat pump solutions, available for industrial type buildings?
Oh, and yes, absolutely. So the ones I showed earlier, big commercial heat pumps by people like Clade, Carrier, Train, lots of others that if anybody's listening, I'm sorry if I've missed you off, but they are industrial heat pumps specifically for large commercial and industrial buildings. So for example, well, I showed the big glass houses earlier, but you could have a factory that's doing some kind of process load. There are no heat pumps. I'm willing to be shot down, but so far I'm not aware of any heat pumps that will do above 100 degrees C. So you're limited at 95 degrees C for process heat, but yes, you can get both air source and ground source, which will do temperatures up to that. And 10 megawatts, 20 megawatts.
Great. Well, thank you very much, Laura. I think we're sort of on the 1 hour mark now, everyone. So yeah, apologies if I've not got round to asking your question. If you'd like to pop it across to Laura, I'm sure she'll be happy to help. And I'd just like to say thank you, everyone, for joining us today. Yeah, really appreciate your support, and I hope you found it interesting. So thank you very much.
Thank you.
All right. Thank you. Cheers, everyone. Yeah. Lots of thank yous, Laura. Coming through, there was just one quick question there from Massey's, that a copy of the recording. The copy of the recording will be distributed. So I will add my email and it should be available on the CIBSE Merseyside and North Wales page. We'll arrange for that to be uploaded. Great. Well, I think that concludes it. So, yeah, thanks very much, Laura.
No problem.
Appreciate your help once again. And yeah,
I'll see you soon.
yeah, I'll be in touch. Thanks very much.
See you later.
Cheers.
Bye. Bye.
Bye.